let's start. Let's start with the final session where everything of today comes together, especially the combination of the two, which is a famous song by Janis Joplin, by the way. An idea for the DCHM lecture series. I am Hans Akkermans from Amsterdam, but I'm also adjunct professor in Tamale in the north of Ghana. I would like to introduce all three panelists at the same time now. For a specific reason that I will explain. The first speaker is Frank van Harmelen from VU Amsterdam. He has a very long history and actually took his PhD in Edinburgh, which was the main site of AI a long time ago in Europe. His field, that is important in this case, his original field is logic-based, hardcore logic-based knowledge representation and reasoning. He worked for quite some time in the famous Common Cats methodology group of Bob Wielinga. And I think most of his work, for which he is well known, is related to the semantic web and related ontology and ontology languages. I think now he is working, that is also interesting, on a very big long-term project called Hybrid AI. And paradigmatically, we were wondering what that hybrid is. We have two panelists. First, Professor Brigitte Krenn. She is a deputy director of the Austrian Research Institute for AI. Her field is very much natural language processing, computational linguistics, language learning. So very much in the language field, very different from what Frank is doing. And our third panelist is Professor Gerhard Friedrich. His key field in Klagenfurt, his key field is, if I may say so, especially intelligent systems for production, engineering, and so on in industry. And he has worked, for example, with Siemens on developing intelligent systems that could be used in production, probably control, in industry. So these are all AI experts, but coming from very different angles, and therefore I think they can give us a very interesting perspective on these issues of symbolic versus sub-symbolic AI. And with that, I give the floor to Frank.
Thank you. Thank you, Hans. Thank you as the diehards to really stay till the end of the day. It's getting somewhat emptier, but so thanks for staying. And we're going to do this in the proper Marxist way. Namely, we had a thesis, we had an antithesis, and I will try to do some syntheses. So the title that was suggested was Coexist or Combine. Actually, this morning, also a comment of Luc prompted me, maybe the title should have been Compete or Combine. Right? And you won't be surprised by the answer, but we'll see how we get there. First, let me reach back all the way to the first presentation in the morning. It's a very interesting historical perspective on the development of AI and the current directions of travel. Sometimes the sort of the simple one-liner that you hear about the history of AI, also in newspapers, is this one, which I call the stairway to AI heaven, right? So the stairway to AI heaven was, well, a long time ago. We were here in the dark and we were doing old-fashioned AI, and now we are on the stairway to we're seeing the light. You know, it's deep learning, statistics, large data. It's a linear progress from one to the other. Okay. And actually, I'm not making this up. Hans sent around, just when I was on the train yesterday from Amsterdam, he sent around just a paper from the recent edition of Communications of the ACM, right? November this year. This is the linear history of AI, right? Expert systems, okay, then we fix the knowledge engineering bottleneck by switching to machine learning. We fix the feature engineering bottleneck by switching to deep learning, and now we are apparently have arrived at general intelligence, okay? So I think, exactly, I'm very happy that you are all nodding no, and this is not how AI developed in this sort of this linear stairway to the heaven of general intelligence. I think you also put this morning a much more nuanced view where you say, well, AI has been widening and shrinking, and it has been shifting. That's a much more nuanced view than this single linear view. I would also like maybe to propose another metaphor, which is that the history of AI is a pendulum, right? And it kept swinging between these two modes of thinking, right? Between the neural statistics, sub-symbolic, and the symbolic knowledge, logic, and reasoning. And roughly the frequency of this pendulum is about a decade, right? And clearly, it's clear to all of us that the pendulum is currently swinging very far now to the left, right, left for the viewers. And I think actually the challenge will be, can we finally get this pendulum to stop in the middle somewhere, rather than keep doing this? Okay, so here's my three-liner on the directions of travel in modern AI. First, major breakthroughs in machine learning. I mean, I don't need to spend any words on this. Now, the previous speaker did a much better job than I ever could, right? So that's totally clear. But maybe a little bit less on the vision of the average journalist is that there's also been a major scale-up in knowledge representation. This was already alluded to by Axel. Where are you? Yeah, there. Right. So now, so let me say also a few words about this. Right. So you all maybe, some of you maybe remember Psych. So this really large enterprise of building a knowledge base that would represent basically everything we know. And the goal was there to use a very expressive language that was so expressive we could express everything. Actually, the direction of travel in KR in the last 10, 15 years has been the other direction, is we make representation languages that are super simple so that we can scale, right? And in particular, these knowledge graphs that Axel also mentioned, a knowledge graph is a super simple structure. It's a network of relations between things. The nodes in the network are the things, the edges in the network are the relations between them. Right, so here we could ask, could Rachel help Jeff with his iPhone problems? Okay, well, answer yes, right, because. And then there's a path in the network that explains that they are both iPhone users, so then maybe she's able to help him. Right, so queries, we can do inference over these knowledge graphs. Right, and they enable a logical reasoning. Logical reasoning of a form that is simple, cheap, and scales. Actually, it scales so well, right? We are now no longer scared, even on university hardware. We are no longer scared of knowledge graphs of tens of billions of relationships. Okay, so we in our lab we manipulate probably one of the largest graphs. It's like 15 billion edges. Okay, between tens of billions of things, right? And these are in use at major industries. And this is just one part of a big slide that I maintain of all the logos of companies who are using this to do business. Right, from Renault, the French car company, to Amazon that's selling everything on the planet, to the BBC, one of the best news outlets, to the Deutsche Nationalbibliothek, you name it, they use knowledge graphs. Right? So this has also really been a major scale-up. And it turns out that both these major breakthroughs in machine learning and in knowledge representation have complementary strengths and weaknesses. Now, this has been alluded to today a couple of times, but I want to spend one slide on unpacking that a little bit. Right? So what are these complementary strengths and weaknesses? So, first, construction cost. Now, as again, it was already also mentioned, now also in the historical talk, the knowledge acquisition bottleneck. It's hard to build these knowledge bases. Actually, these days we don't build knowledge graphs by hand very much anymore. We use machine learning to build knowledge graphs by extracting information from textbooks, from scientific papers, from databases. But still, it's expensive to build them and to make them at high quality. Right? But of course, the statistical techniques also come with their cost, namely the data acquisition bottleneck. Right? I'm always a bit annoyed when machine learners tell a doctor, no, I can't help you with your problem because you don't have enough data. Right? I always think, no, you have the wrong algorithm. Right? So this is a real limitation of much of the deep learning techniques, that they work very well in domains where there is sufficient data. So that's the construction cost there. Knowledge-based systems, no, they suffer from this combinatorial explosion. They get worse with more data. As I just said, these statistical systems get worse with less data, and they suffer from the sample inefficiency. They need unreasonable amounts of data. Right? Reinforcement learning was mentioned earlier today. I think is a prime example of where machines need unreasonable amounts of data to get trained. Somehow humans and other animals manage to do this much more efficiently. Explainability, of course, is one of the big trade-offs, right? Was also mentioned. And the generalizability. So we're all very familiar with the performance cliff of symbolic systems. If the answer is somehow derivable by your system, you get a perfect answer. If it's not derivable, you get no answer. And there's very little middle ground, right? That's a very steep performance cliff. If it's outside the scope of the system, the answer is don't know. Actually, the statistical systems also suffer from a generalizability problem, namely this out-of-distribution data. If you're trained on one distribution, they are not very good at making predictions on data that is outside their trained distribution. We'll see an example of that later. Okay. So there is really this set of not only different strengths and weaknesses, but even almost complementary strengths and weaknesses. So then the obvious thing to think of is, well, let's combine the two. Can we get the best of both worlds by combining them, right? And this is what is now known as a neurosymbolic AI. And what I want to do in the main part of the talk is just give you a glimpse from the factory floor. So what people in our lab are doing, just a few examples of how you would combine these two. Because many people have today said, well, we should combine them. Well, okay, I will unpack the box a little bit. But how can those combinations, what can they look like? And it's some of the work in our own lab and some of the work in the literature by others. So the overall working hypothesis of neurosymbolic AI is that these two approaches have, and I didn't use symbolic and sub-symbolic because I'm dreading the question, what is a symbol? Right? So I characterize them as knowledge-driven and data-driven systems. Now the hypothesis is they have strengths and weaknesses. These strengths and weaknesses are complementary, and we need to combine them, right? So that's the end of the compete idea, right? So under that hypothesis, actually this is not a new idea, right? We think, well, this is maybe a new young baby. This is a baby with a beard, right? So they already, depending on which survey you believe, this baby has already been around. This new idea of neurosymbolic AI has been around for 20 years. Another survey says it's been around for 30 years. Right? I don't know what. I think even the Dartmouth a proposal that you had on the screen this morning had already traces of that. Right at the beginning of AI. So this is not a super new idea. And somehow we have been suffering from this idea that there are two churches and you're either a believer in one church or you're a believer in the other church, right? So, if you're a machine learner, you're a machine learning algorithm, and now you need to classify this object, okay? Well, you might say, what is it? Maybe you'd say it's a flower. If you're a bit more sophisticated, you might say it's a rose, right? But in any case, you would be wrong because it's part of a chair. It's a cushion. Okay? So what went wrong here is that you didn't take into account contextual knowledge about the objects that you are classifying, right? It's not just the property of the object, it's the property of the context. And this is one of the things that, that we can encode in background knowledge. So context-aware machine learning, what would we do? So let's assume that we already know the object in the blue bounding box, namely we're looking at the chair. Now the question is, what is the object in the red bounding box? Okay, and our background knowledge would tell us that a simple ontology of actually a mereology here of furniture would tell us that now cushions and the armrests are the parts of a chair. Right? This is not a very good mereology. Actually, it says the only parts of a chair are a cushion and an armrest, right? And this will give us a prior probability saying, well, given the fact that we're looking at the chair, the probability that we are looking at the cushion is much higher than the probability that it's looking at the flower. Okay? It's not zero that it's a flower. It could be a flower lying on the chair, but the background knowledge tells us this. So this is, in a way, semantic information about the context that we can use as bias, in a way. Actually, the term that is used for this is a semantic loss function. So we all know what is a loss function in machine learning. It's the difference between the answer you get and the answer you want to have. And that's you're trying to minimize the loss function. Now that's the incentive for your machine learning algorithm. Now, gradient descent over the loss function. Now we have two loss functions. One is minimizing the difference between the answer you get and the answer you want to have, so the data loss. And one is trying to minimize violation of background knowledge. So we have background knowledge, and we're trying to minimize the violations of the stuff that we know about this world. Okay? And seeing that it's a flower is a bigger violation of background knowledge than thinking that it's a cushion. Okay? So we now have a double loss function. And actually there is already a 2019 survey paper where that surveys more than 100 different machine learning systems that do this semantic loss. That's now a very popular way of encoding domain knowledge into a machine learning algorithm by encoding it in the loss. Right, so here is another reason to do this combination of symbolic or data-driven and knowledge-driven learning. This is a first-year programming exercise in an AI class. Okay? This is called MNIST addition. MNIST because that was the database with all the handwritten digits. And it's addition because the task is the system has to learn to recognize the digits and compute the sum. Okay? And it's a first-year AI course programming exercise to train a neural network to do this. Okay? So it takes a bunch of pixels as an input, right? 2 times 7 and 84 pixels, and out comes the number 8 in this case. I don't know about you, but for me this feels like the wrong way around. Right? So in my head, two things are happening. I'm recognizing the digits, and then I'm adding the numbers. I'm not using the pixels to compute the sum. Right? That seems like we've missed the intermediate abstraction. So this is an example from Luc de Raad's group in Leuven, where in their Proplog system, what they do is they train two learning functions. One is a learning function that sees the digit and turns into a number, and then a learning function that takes the two numbers and adds them up into 8. Okay, so what have we gained? Okay, we have gained that we are now much more robust to change. Because if suddenly the pixels are no longer white on black, but they become black on white, right, you can throw away your entire neural network, right? Because the function has been completely merged into the single neural network, right? So you have to retrain the entire network. Whereas in this setting, the one that they do in Leuven, you only have to retrain the C function because the addition function remains the same, thanks to the intermediate abstraction that we have injected into the learning machine. Okay. One more example. This is a little bit more sophisticated example about learning that is robust to change. This is work by people at UCL and DeepMind in London. The AI people in the room will recognize that this is a reinforcement learning loop where we have an agent. And the agent has to learn certain behavior. How does it learn the behavior? Well, it does something in the world, the motor output, like it moves a block or it makes a step. And then two things happen, namely the state of the world changes and it gets a reward signal. It observes the state of the world. Maybe the block has now fallen off the table and that gives it a negative reward, right? Or maybe the block is nicely on top of the other block, it gives it a positive reward. And by going through this loop all the time, is basically how you train an animal, right? You give it a reward and then it learns to do the right thing. And then this is typically the standard way of doing this is with a single neural network as the brain of the agent. And we train the neural network by doing the right thing, going through this reward loop. And they said, well, what happens if we equip the agent not just with a single neural network, but with a combination of a neural network and a symbolic representation, in the same way as the Leuven people did, namely a neural network to learn the digits, and then the numbers to learn the addition function. So a neural a backend, yeah, I think they called it backend and frontend the wrong way around, but that's just me. So the neural end which observes the world, which then produces a symbolic description of the world, and then the symbolic description of the world is used to decide what the next action is. Okay, how do we know that this is a good idea? Well, we run experiments. So here's the experiment they run with this architecture. So this is a grid world. The plus in the middle is the agent, and the agent can move around in this world. All it can see is the pixels on the grid, and it has to learn to collect all the crosses and avoid all the zeros. Okay? So it has to move around. Every time it picks up a cross, it gets a point. Every time it hits a zero, it dies. That's what it has to learn. And you see that the classical deep learning, reinforcement learning, the blue line, is much better than the symbolic agent. Okay, so that was bad news for the neurosymbolic people. But then they did something interesting. And they said, okay, let's shake up the world. Let's change the world. So now we change the world. So for example, it's no longer a grid, right? And then every so often we change the world. Right? It turns out that now the symbolic agent that doesn't learn to observe the world in terms of pixels, but that can observe the world in terms of objects and spaces between objects, and one object being behind another, those spatial relationships, it is much better at adjusting to a constantly changing world. Okay? So this abstraction really buys us something, this symbolic abstraction. Just as with adding the numbers. Okay, I mentioned out of distribution data. This is my favorite example. I mean, it's really great. It's a bit older, but still, the image labeling competition. What is this lady wearing on her head? 99.7% certain she's wearing a shower cap. Okay, we all know it's not a shower cap. Even the people at the back, who can't see very well what she's actually wearing on her head, right? You can still recognize who this is. Right? And you know that whatever it is that has got on her head, it won't be a shower cap, because she's the queen, or she was the queen. So how can we compensate? And what went wrong here? Well, you can see what went wrong here. In the training set, of course, the machine was trained on lots of images of people wearing clothes, and it has to do object labeling. There were probably very few or none training images of a woman wearing a crown. Okay? But there were probably lots of images of women wearing a shower cap. So then all it can say is, well, it's probably a shower cap. This is an out of distribution data element on which it produces a poor result. So how could we now compensate this? Well, we do what you did, namely you use your background knowledge to decide that whatever the answer is, it's not a shower cap. Right? That's not a visual conclusion. That's a symbolic conclusion that you know by deriving from background knowledge. Okay, so this is the problem. What's this thing on her head? We use a neural network because clearly neural networks are the right way to do vision. I mean, nobody in their right mind will do symbolic processing for image analysis. And the neural network, as it always does, it gives you a ranked list of outputs. Right? Okay, then we take a softmax and we pretend it gives you one answer, but it doesn't. It actually gives you a whole range of answers. And then we use background knowledge, a knowledge graph, that tells us that there's actually a very close relationship between queen and crown, and a very uncertain relationship between queen and shower caps, if at all. And that would give us a reason to readjust the ranking that our neural network comes up with. Right? This is what we do all the time. if we're in a noisy environment, so you cannot really hear what your friend is saying, and you think they're saying something really weird, right? They can't possibly have said this, right? So it's your background knowledge that is then telling your audio system to go back and think again. So that's exactly what's happening here. By the way, these knowledge graphs, now they are really big. So Doug Lennett's original goal was, I think, as you said over lunch, was to encode all encyclopedic knowledge. Okay, consider that solved. Okay, now the entire DBpedia is now a small part of Wikidata, right? So all encyclopedic knowledge is in a knowledge graph, and if it isn't, it's because we just haven't done it yet, because we know how to do it, right? So, and that's not the only thing that's in a knowledge graph, but this kind of stuff. Now, the relationship between queens and crowns, it'd be trivial to query it. We can use actually the same architecture to fix another problem that we are suffering from, namely the lack of explanations. So, now, why is this a crown? Okay, well, it's a crown because she's the queen, and queens wear crowns, right? So I deliberately did not call this an explanation, because it doesn't explain how the model worked, right? It is a justification of why this is a reasonable answer. Personally, I'm now going to offend a few people in the room. I think a lot of explainable AI is climbing up the wrong tree. They're solving the wrong problem. They are solving the problem of explaining how the model got to the answer crown. The only people who care about that are machine learning engineers, right? Users don't want to know how the network got to crown. They want to know why it is a reasonable answer that it's crown, right? So when this morning, when I came from Hauptbahnhof, I could take the subway or I could walk, right? And you asked me, well, why did you walk? Okay, then you're not interested in the neural activity that led me to one thing or the other. You're interested in some justification of why I chose. I needed some fresh air after being in a night train for 12 hours, right? That maybe wasn't even in my head, but it is enough for you as a justification. And these justifications, they come from symbolic representations, even if the symbolic representation is only loosely coupled to what happens sub-symbolically, etc. Right, so I hope you get the point now. And I'm doing precisely what Gerhard asked for this morning when he said we want architectures that combine neural and symbolic, right? And these are all different architectures. So there is not a single answer here, right? There is lots and lots of different ways of combining them, and they give you different benefits. So we should really explore that space and build a theory about that space of combining those two families of systems. Okay, and actually the group of Marta Sabu is right at the back here. They did this amazing Herculean task. They annotated 300 plus papers from the neurosymbolic literature and drew the architecture for each of those systems. Right, so they have now this huge annotated collection of 300 systems in a few dozen different architectures of how you can put these symbolic and sub-symbolic components together. Right, so this is really on our way to building a theory of how to build those neurosymbolic systems. Okay, so summary, and then there's one small part about the elephant, another elephant in the room. You mentioned one elephant in the room this morning. There's another one. The neurosymbolic paradigm enables AI systems that are, we've seen, explainable. We can use this, I didn't show this, but we can make them guaranteed safe, because safety properties lend themselves often to symbolic expressions. Right? I don't want two trains to be in opposite directions on the same train track. Right? And we can, any neural scheduling system had better guarantee that this will never happen. And we can impose these symbolic constraints on the neural networks. Or we can encourage them as part of the training, different architectures. I show you they can be aware of context. They're more robust against data drift and out of distribution data. I didn't show, but we also have good examples of how knowledge-infused systems perform much better on small data sets. rather than big data sets. Essentially, you give them very strong effective bias. Okay, so what's the elephant in the room? Well, the LLM in the room here. So the whole talk, I haven't mentioned LLM yet, right? You must be getting impatient now, right? So has he not been paying attention? So yes, let's talk about LLMs. By the way, you can tell that this is a generated image because most of these people have one leg. Some of them have no hands. Some of them have really scary zombie faces. Sorry? Diversity, right? We want zombies in the boardroom, exactly. No, but seriously, no, they are really impressive stuff, right? I mean, I couldn't draw this to save my life. So no, they are really I'm not out to belittle them. I'm just out to kind of characterize what they are and what they are not. Okay, so in AI we are really bad at giving really stupid names to things, right? So things that are completely overblown, overselling, including the name of our field, by the way, right? So I tell my students AI stands for Advanced Informatics. But for once we gave a good name to something, because LLMs are language models, right? They are language models. They are not world models, right? Because so an LLM person would say, well, why do we need this symbolic stuff? Because these LLMs work perfectly fine. They don't need any symbols. Why would we need any symbols? Well, the problem with LLMs is they are language models. So I grab back to what's called in cognitive science the representational hypothesis, right? And I'm going to read it out to you. And this is sort of widely implicitly shared by cognitive scientists. Cognitive processes are mediated by internal representations of information, and the mind operates by creating, storing, and manipulating mental representations of the external world, okay, to guide perception, reasoning, decision-making, and action. You'll have a very hard time finding a cognitive scientist who disagrees with this. Interestingly, they are neutral. This is neutral on the nature of what that model should look like, okay? So the neuro-symbolic, the synthesis that I promised you at the beginning of the talk, right? Thesis, antithesis, synthesis, is that AI systems will need world models. And these world models, we don't know what they will be. They will be partially symbolic, neural, distributed. And if you want to recognize this face, you better use some of those. And then reasoning about those representations will be network activations. And they will be a part of these internal representations will be symbolic, propositional, and I don't mean propositional as in propositional logic, but propositional as in propositions, as in language. They could even be language itself, right? And then reasoning amounts to symbol manipulation, right? But reasoning about the world is not the same as reasoning as reproducing linguistic patterns, right? And this is the ultimate source of hallucinations. Now, the previous speaker said the same thing. Right, that these machines cannot help themselves because they reproduce linguistic patterns. They are language models. They are not world models. What the world model is, I would be surprised if we find a single language for the universal world model. My money would be on a happy zoo of different representation languages and different algorithms that work on these representation languages in the style that I just sketched. Right? But don't forget, we need these world models and algorithms that operate on them and not just reproducing linguistic patterns. Okay, thank you very much.
Thank you very much. May I invite Brigitte to give her, let's say, co-referat. There are some slides. Could you put up Brigitte's slides?
Okay, I need that one, yeah. So this is the uninteresting part. This is just Freiung in Vienna, where ÖFAI is located. Sorry. And now I'm just giving you...
They will switch it on.
Hello, is it on? Okay. That's from linguistics and what we also used in computation linguistics. So I've started with computation linguistics in 1989. So that's quite a long time, and I'm still working in natural language processing. So why is natural language so difficult for machines? Because we have ambiguities all over the place. So those who have a bit of education in natural language, in linguistics, you know these world level ambiguities. Time flies like an arrow, but fruit flies like a banana. And we have those different parts of speech where flies is in one context is a verb and flies in the other context is a noun, and depending on that, the meaning of the word is different, and the syntactic structure starts to become different. We also have this well-known word, phrase level ambiguities, where the syntactic structure, so linguists tended to think in trees. Why did anybody ever think in trees? Because we had these grammar theories and we needed to formalize the grammar theories. So we needed to have some formalization or representation, formal representation, which was workable. And trees is something like that, which is workable on a machine. And so we have this, I shot an elephant in my pajamas. So who was in the pajamas? Was it the elephant or was it me? And depending on the syntactic structure I have, the meaning is different. Who is wearing the pajamas? And also it's different what the meaning of shoot is. If you look at the picture, or the two pictures, shooting with a gun or shooting with a camera. So we have lexical semantics, and back in 1991, we really tried to add lexical semantics and semantic nuances into a lexicon for machine translation. It was devastating because the ambiguity of our representations exploded. And so we got a number of sentences, representation structures we needed to translate into the other language. So we threw out those variations and variants again because we just had an explosion of ambiguity. So what else? We have these discrepancies between competence grammar and language use. So the idea of every speaker of a language is an expert in the language, and linguists formally tend to ask people, give them a sentence or an utterance and then say, is this a correct sentence according to your knowledge of the language as a native speaker? And then so you get it into the competence grammar. But when you look into a text, something what is produced in a newspaper or an online newspaper or in a comment, a post, whatever in social media, then you won't find just competence grammar representations. So you find a lot of spelling errors, typos, sloppinesses in punctuation, mixing of languages, so German with a lot of English words interspersed. We find characteristics of spoken language in written text. In the speech, when we do speech analysis, we find omissions, hesitations, fresh starts, dialectal varieties, etc., etc. So there is a lot of, and when we go into meaning, we have, as I already told you, the lexical representations and these ambiguities we get with the nuances of word meanings, and then we have the morphosyntactic ambiguities. We have pragmatics. The same sentence or the same utterance may mean different things, like, oh, it's hot inside. That could be that I'm asking somebody, please open the door or turn down the heating, or it's just, well, I just say it's hot inside and that's it. The literal versus a metaphoric reading. Everybody knows kick the bucket, but I could kick the bucket, you know? And where's this difference? And we also have language grounding. So we have somebody speaking, acting in a situation. And when we look into what is in the language, when we are in a situated context, there is so much not in the language because it's there, it's on the table, we see it. We don't need to tell it that there are 2 glasses on the table, because everybody who is in the room and looks at the table knows it. I do not need to have it in my language. And that's those few slides I showed you, a lot of reasons why it's impossible to put all this knowledge you need to sort of represent into rules, sets of rules. So when I started out, so this, in the internet you find a lot of those timelines, where, when, what. When I started out in the early days, like for me it was in the 1989, we were just writing rules and trying to specify grammars, but we were computational linguists, which meant that we had to process everything which just was produced in reality as language, just text at that moment, right? And but this was impossible. So we quite soon realized we need to have data and we need to have machine learning where we can cope with all those errors and tiny deviations of what's the competence grammar. And so we could not live without machine learning. That meant we needed to get onto data, and in 1997 we managed in Germany to have the first German tree bank, by that time called Negra Corpus, now it's Tiger Corpus, but this is kind of 10,000 sentences from a German newspaper, annotated with syntactic structure and part of speech tags and stuff like that. And that was the amount of data we had for learning at that time. So we were in this area of early statistical approaches. And then at the point, and the really breakthrough for natural language processing was this attention is all you need, this paper in 2017, where which is a funny story. The small kid of my Doktorvater, as I did my PhD with in Germany, was co-author. So it was a whole generation later where this came in. And all of a sudden, and now with these large language models, we have natural language processing and generation qualities which are really nice. So the text which is produced is quite good, is very elaborate, much more elaborate than a human could be. So tell me to give my talk in a sonnet form of Shakespeare. Thank you very much. I wouldn't be able, but a language model would be. So, and now we get to what Frank said. AI, artificial intelligence. So we have so many words which are so misleading, and also everybody's an expert in language. So everybody is super impressed by what these language models can do, but all the grounding, all what you need for understanding is really far away. And so this is my last slide. So what language also is. So I started out with text. I was interested in semantics, but semantics was a disaster. So I stayed more in syntax because this was more easy to handle. And at some point, I got back to what does it mean? What is language? What does it mean to understand language, to produce language? And you have this situated cognizer. You have a system which has perception, which interprets the perception according to the context the system is in, and which sets an action, which again is perceived by another system, which makes its interpretations and so forth. So we have this loop, and in order to do this, we need sub-symbolic machine learning approaches, because all the perception, it's really, really hard to have a vision, to see what's in the room, to understand what has been said. So this is helpful, but for deciding and interpreting what it is, we need some symbolic approaches. So it doesn't work without. Or we need to find good ways to get this, what we now call symbolic information, into the machine learning process. But I think this is, in order to have language understanding, you really need to have this bigger understanding. So for the semantics of objects, we are already quite fine with these multimodal models. So it's almost impossible when it's impossible if you say, okay, this is a table, it has legs and da-da-da. So this knowledge representation is really hard. But if you have visual informations, so embeddings of visual and linguistic knowledge or linguistic data on a table or on many tables, you can deal with these variations which are there, which you cannot really specify in rules. And so you have it in the embeddings and you have the knowledge. But there is so much which is going on in this interpretation part, which is much closer to a rule-based approach. So thank you very much.
The floor is to Gerhard.
Thanks. So the slides, someone should. Okay. Good. So, yeah, my name is Gerhard Friedrich. Thank you for staying so long. I try to be brief, and I will tell you some dirty little secrets which are not usually talked about. So please switch off the recording. Okay. So.
You press on the down arrow.
Ah, thanks. So why should we combine? So currently, if we look at our applications, when we apply AI, so especially symbolic reasoning, the user specifies the problem, and very clever users apply KR so that a computer solves it. Okay, so basically, it's not actually about AI, but it's about clever users using some methods of AI currently. Okay, so here you see electronic system, a very big one, okay, which we have to configure, so comprises 50,000 components, 200 racks, and so on. Okay, so really huge. But actually what we want to achieve in AI, hopefully, we can agree on this, that we want to go towards broad AI. So the user should specify the problem and the computer solves it. So this was the original vision of AI, okay? And we are still not there, and I will argue why, okay? So at Siemens, we had at most 10% of the practical problems really can just apply a specification of the problem, push a button, and the computer solves it. At most 10%. Okay, at most. Good. So what we actually want is, well, we cannot expect miracles. You cannot assume that now AI is solving all the MP hard problems just as that. But at least, I mean, it should be possible that by general problem solving, you should surpass humans, right? Why should we actually bother about symbols? Yeah, so usually now currently in machine learning, many says, well, actual symbols are yesterday, so what are symbols good for? We heard this already. So it's about correctness. Yeah. So Frank took the train. Yeah, and actually AI systems took care about the correct engineering of all the safety systems. So this was done at Siemens. So we implemented such a system, and it's operational since the 90s. So actually you want that all the systems are really correctly engineered. Okay, this is an important thing. Completeness, yes, sometimes we have to confess. yeah, if it's small enough. So I will talk about this. Yeah, so this is here. If we can model the system, we can specify the system by logic, yeah, or formal languages. Great. Yeah, do it. Yeah, but unfortunately, it's not always the case. But I want to make a point for reasoning from first principles. And using this to solve new problems, and of course explainability. We heard about this. Okay, so now here comes the dirty secret. So if we use the best symbolic problem solvers we have, okay, for a very simple engineering task, yeah, I showed to you. Then we have the following behaviors. Here are the number. So here is the size of the problem. Basically, here are the number of guesses. Yeah, the yellow one is the traditional system, that currently available. We have this number of guesses. So you have this watch the logarithmic scale. We have this behavior, yeah, for runtime. Okay, and what is even worse, yeah, is that we have this behavior for memory consumption. So, Frank, I'm afraid that additional resources won't help. Yeah, we need all the atoms in the universe to represent this problem.
I don't believe your graph.
Okay.
I see other graphs. So okay.
It depends on the. It's a very.
But ultimately, you're right. You cannot beat exponential growth with linear hardware.
Yeah, it's a very simple problem. Yeah, very simple problem contained in the problem we do in configuration, But if you have the right, and here comes the trick, yeah, if you have the right heuristics, yeah, as humans are applying, yeah, you can actually read through, and we know this, I mean, this is clear, yeah, if you have the right heuristic, yeah, you can reduce the number of guesses, you can save runtime, and you can save on space consumption, okay? The big question is, where do the heuristics come from, right? Okay, and here I think this is the point where we can apply machine learning, and here is exactly the point where we can use the machine learning methods we have. We all know about this, okay? About the big success of machine learning and Go playing. So why do we need sophisticated machine learning techniques? Well, it's about the search space. So in chess, you have 10 to the power of 120 moves approximate search space by 80 moves. In Go, we have 10 to the power of 360. That's much larger. And the problems we are dealing with are very complex manufacturing scheduling problems. Okay, for example, in chip manufacturing, where we have a search space of 2 to the power of 500,000. Okay, and that's increasing, yeah, because the factories are becoming bigger and bigger. Okay, so we are applying machine learning techniques, yeah, to speed up the scheduling, and we are quite successful for small problems, yeah. But currently they don't scale. Okay, it's a big question. How can we further develop these techniques such that they scale for really huge search spaces? And it seems that humans are very good in inventing heuristics. Yeah. So how can computers be good in inventing heuristics? This is a big question. Okay, so it's all about finding the right heuristics. Okay, so next thing I want to share with you is the power of reasoning from first principles and qualitative reasoning. Yeah, so it's because we always claim, well, logic helps you, but how does it help really? Yeah, and one answer is because we can model with logic and formal systems first principle knowledge. How does this help? Okay, so these are batteries, these are bulbs, they can be off, they can be on, we have switches that can be closed, okay, we have lines which are distributing the energy. And you all know the behavior from school, right? Yeah, Kirchhoff's laws. So you learned Kirchhoff's laws not by billions of examples, but the teacher told you how the math works, yeah, and how you model systems. And you can apply some qualitative reasoning. If you have a battery and the switch is open and the bulb is dark, well, this is a correct behavior. If you close the switch, bulb is on, great, it's a correct behavior. Yeah. if this switch is closed, well, you know, this is not the correct behavior. Yeah, I never told you some examples. Yeah, but because of your knowledge, your first principle knowledge, you can easily figure out that there is some error, and you can figure out, well, it could be the battery, or it could be the bulb, or it could be some wires or the switch. But actually, as we know from probabilities, it's either the bulb or the battery. Now, how can you diagnose the system? Well, how do electrical engineers diagnose this? Well, you have to figure out whether or not there is energy. Yeah, how can you figure out whether or not there is energy? Simply put another bulb, in parallel, and it's on. Okay. And I can give you any circuit, and observations, and you're clever enough just by applying first principle knowledge to diagnose and repair the system without billions of examples. Okay, and you are very general, right? Okay, so we are very, very general in all. If you learn by examples, you need billions of different structures, and you never can be sure if your system will diagnose another structure correctly. Okay, so the big advantage here is from reasoning from first principle, model-based. It's called model-based reasoning. In causality, for example, in diagnosis, repair, configuration, we can implement this by a representation language and do some logical reasoning, and it's complete and correct. Okay, great. So diagnosis is solved, right? Check mark. Okay. Well, of course, we have to deal with complexity and so on, but anyway. But the ugly truth is that unfortunately in reality, if we go to real systems, so like you see here, a factory floor, so it's a factory floor of one of our partners, so first Alpine. Unfortunately, the systems are so complex that engineers can give you precise models. Yeah, I mean the rough physics is known, but the precise models are simply not there. Okay, so we somehow have to learn. Yeah, we have to learn a theory about the behavior of the system, which is sufficient good enough, such that we can optimize the system, such that we engineer the system. Okay, and diagnose them and repair them. Okay, so here I see it, an important case, for learning. But it would be interesting not only to learn on a data fitting basis, but it would be interesting to learn really theories, theories which are generally applicable. Okay, so at least these are 2 points where I think we can find synergies between symbols and machine learning. And Sepp already mentioned this. We are working on this very hard, in the cluster of excellence here in Austria. And the goal is to build, to go from narrow AI to broad AI by combining the sub-symbolic and symbolic methods. Thank you very much.
Thank you very much, Gerhard. Please. Yep. I would like, could I have the last? Yes. Because this is a workshop on paradigm shift with a question mark, I would like to discuss the issue of paradigms, because it has been mentioned today, but not really discussed. And Frank already showed that. I was in the train to Landstraße, and I read this recent article in the last issue of the Communications of the ACM, which is a very well-known magazine, especially with computer scientists. And this is actually the article, the paradigm shifts in artificial intelligence. And it makes quite a number of claims about... The diagram I showed. Yes. May I have the next slide then? Let's see.
Yeah, here's the diagram.
So I picked the most telling parts of the article. It's by a US business school professor. And basically he uses Kuhn's paradigm theory to give a history of artificial intelligence, a a very different view on history than Thomas Haig has been presenting this morning. So really his idea is there is a linear succession of paradigms, and in the beginning we were just doing something, and then we had a breakthrough and we doing more, and now we are at the level of general intelligence. We have heard this story before, so I'm a bit sarcastic about it, but this is really what is presented. And he names actually this after the important things. So expert systems, machine learning, deep learning, general intelligence. That's basically his claim. I would like to say something about Kuhn. What he does is use a very specific interpretation of Kuhn's theory, which you often, I think it's very simplistic. And Frank joked to me, I will be a senior fellow at the Institute of Human Sciences, that I have drifted away very far from my original roots, which are actually in the theoretical physics of nuclear reactions. And I would like to ask, from a physics point of view, a number of questions to the panel. So first of all, and actually, all Kuhn's examples are from physics. First of all, if we talk about paradigms, what is your reaction to this linear succession? And if you disagree, what are the elements that you would make different?
Okay, so I think it's hard to argue against the boxes, right? So I recognize the boxes as different schools of thought, and that the different schools of thought were also more or less dominant in different periods of time. What I argue against is these linear arrows. And so I think the boxes are recognizable. I think these arrows are oversimplification.
I mean, machine learning. Sorry. Yeah. We need another.
Yeah. Just a comment. Machine learning and deep learning are not really different paradigm. I mean, it's so. This is oversimplification,
right? And I think I said I won't argue about the boxes. I will argue about the last box, right? This is a general intelligence. But I do think that something really important happened at the end of 22, right? So this emergent behavior that we get at scale from these transformer models, nobody had predicted this, right? The paper was around for 5 years. And in a way, all they did was pump more energy and more data into that architecture. And then we really got this emergent behavior. As an outsider, I now think natural language is a solved problem. Right? I'm curious what you... and I think that is a real breakthrough event. So I think we have gone through breakthrough events, and a recent one was the emergent behavior of LLMs, but this line is too simplistic.
Brigitte.
Well, I don't think that's a solved problem, not because I need more reasons to work, no. But I think, yeah, it depends what you mean by natural language. So if I want text clustering, information extraction, stuff like that, yeah, of course that's it. And dialogue, it's solved, but solved in a way. The system still does not understand. Imagine you have a robot in your house, and this robot, you tell the robot, say, go fetch the milk. The robot has maybe a map already, and the robot needs to learn. So in Japan, you have the same robot, and it needs to understand Japanese. And if you have a funny language, it needs to understand what you mean. Do you give me that bottle? I need things like that. So you have to natural language learning and understanding what is really meant, and the grounding. I think you cannot do just with believing that we have text, and we have all sorts of text in huge masses, and text are representations of the world we are in, and that's why we understand the world. So I think that's really the debatable part. So some people believe that you just train more data and that's it, and other people say that this qualitative jump is not just in this. Yeah, and if you work with LLMs, so what do people do with LLMs these days? They treat it as a kind of a specific kind of animal and do some studies, some psychological studies, some social studies, some communication studies, and then see what the system says, and then do a bit of reasoning and do a bit of chain of thought and things like that. But you get it very quickly. You see that this is a babble bot still. Yeah, it's talking, but
I think this is the point about it doesn't have a world model, so it doesn't know what it's talking about.
Yes,
but
and it doesn't. Yeah,
talking is solved.
Yeah, of course, talking is solved. Yeah, definitely, but
okay.
that's not that natural language, because there's much more in natural language, because this is communication, interaction.
Gerhard.
Thank you. I'm not sure about the question.
Well, do you recognize this history of AI?
Yeah, I'm not sure if it's history. Yeah, maybe. Yeah, if you think this is a history, okay. I'm. Oh no, I'm not very sure. No, but I think. I mean, there is a jump from deep learning to general intelligence. It's just my opinion. Yeah, I think there will be a lot of boxes. Yeah, now from deep learning to general intelligence. Okay, but I think the more interesting question is: do you believe? Yeah, do you believe that something like general intelligence or something like near general intelligence will be possible at some point in time? Okay, I mean, we have researchers which say, well, it will be. Yeah, Benjo, for example, is a good point. Maybe you will ask, do you believe? Yeah. So and well, when you know this by the statements by Hawkins and yeah, so I thought this complete mad. I mean, come on, yeah, because you play Atari games, yeah. Why should this be a threat? But you know, I have to rewrite every year my slides where I try to show the students that there is no common sense. Yeah, there is no common sense in large language models. Yeah, they're improving on common sense, and it's really astonishing that by such a schema, yeah, you can mimic something like common sense. So this let me think, yeah. So I think there is a divide now in the researchers. So some believe something like general intelligence compared with and combined with robotics will be possible. Some don't. And if you don't believe, then you live in a happy world. Yeah. So just keep going. Yeah. But if you believe, okay, that something will be possible, then the big question is at which point in time we should act, okay, in order to prevent bad things will happen. So I'm not on the side of SEP, yeah, saying, well, we do the objectives and we set the goals, yeah, and nothing will happen. You never know who is setting which goals, okay? And you know the story of Midas, yeah. Maybe the objectives turn around, yeah. And you all know the HAL, yeah, the computer, yes. And maybe there are some hidden objectives you don't know. So I think so. The bottom line is if we think that something is going to happen, yeah, which will become near as good as general intelligence, it serves or mimic human behavior on a very intelligent level. Compare and do this and integrate this with robotics. Yeah, I think that there is a point in time where we should start to think quite a lot. Yeah.
Thank you.
Thanks, the panelists. My name is Thi Huang, and I'm not from the field. I think the most I did was researching and writing about how technologies interact and shape organized crime, like human trafficking and cybercrime. So I have a questions for Frank. As someone who's not from the field, thanks for your presentation. I think it's quite easy to follow. I've got the questions about your graphs regarding the X and O's, like the tic-tac-toe sort of. I'm quite puzzled. Why would a structured X and O's graph, I mean, if you could go back to that slide, it would be great. Why would the symbolic AI predict and did better than the neural sort of symbolic AI in an unstructured world?
Okay, so maybe I wasn't very clear in the example. So what the sub-symbolic agent does is it has to make a direct mapping from the pixels in the world to the actions it does, right? So it sees pixels in the world, right? Some of them are white, some of them are black. That's what it sees, and it has to map these pixels in the world to actions like how to move to get all the points. This is the same as like seeing the pixels of the numbers and then having to come up with the answer 8. And what feels more natural is that you create an abstract representation of the world, not in terms of the visual pixels, but in terms of objects and relationships between the objects. And then you navigate in terms of the objects and their relationships. And it turns out that abstract representation is more robust to change. Every time the pixels change, your network loses if you only think in terms of pixels. But if the pixels change, you rebuild the abstract representation, you can reuse everything you've learned about navigating in space. That's so if Gerhard just now moves from here to there, I don't need to relearn how to avoid not walking into him. Right? I have abstract notions of objects and space.
Olga.
Yeah, the more I listen to this discussion where we have arrived now at the end of the day, the less I'm convinced that we are really talking about paradigm shift.
Hi.
When you go back to Krenn, just to remember, first of all, it was only about physics. That's correct. Secondly, we should remind ourselves that the advances of physics were very much based on predictions. So physics advanced because you had people coming forth with theories that make predictions, and you had experiments that would prove this hypothesis or this prediction was actually correct or not. And therefore, the paradigm shifts that Krenn talks about were centered on the emergence of anomalies. People made observations, and they started to realize that what they observed started to derive more and more from what, the paradigm, the dominant model at the time would predict. So something must be wrong with it. And then, and this was the big really discovery of Krenn, was that there was not some kind of, world spirit moving physics along, and knowledge would just accumulate, etc. But he was very clear in saying it was the cognitive consensus of the group of physicists who said, well, our model, our paradigm, the dominant model, does no longer confirm to what we are observing. So something must be wrong, and therefore we have to come up with something new. But what you are discussing, what we are discussing the whole day, is very far away from that.
Let me try.
Wait a moment. We are grappling with finding a way of retracing the history of the field. We started out with Tom, and he gave us one, very well-covering things, but then we heard, well, he does not look at what happened in Europe or in Japan or, other places of the world. Then, you come up with different phases and you say, well, but at the same time, things happened here and there, and this does not really fit. So it's much more messy. It's not only not linear, it's messy. And we are dealing with the messiness of the way how a field developed. And I think this is what we have to grapple with and find a way of making some kind of order, getting some kind of order into this messiness that follows a vague timeline, of course, but you can also see, when I mentioned funding in the morning, it was not just to say who funds which project, but what is the impact of funding? Why did priorities change? Why did some governments, give funding for this and then they stopped it because new priorities? And all this has a relationship with what researchers were doing, the way how they were presenting their work, but also, they came up with new ideas, and some ideas, just did not lead anywhere. So we also have to look at the roads not taken, I think. So, I think we have a lot of work to be done in front of us, rather than following this, in my view, very speculative idea about general artificial intelligence, which diverts so much of the concerns. In my view, it's really a deliberate way of diverting us of problems that we face today.
So I agree about let's not get distracted into general intelligence. But in a way, we are making predictions in our field. I mean, the crowd. Let's take natural language. In a way, your first slides, the natural language approach from the 80s, is making a prediction. Namely, the prediction is rule-based grammars are a good model of natural language, and that's a prediction that turned out to be false for the reasons that you described, and people made another prediction, namely latent distributed neural representations that we can learn instead of code are a better way of describing natural language. So I think there is, in a way, a sense of we are predicting something and then we are failing or succeeding to confirm that prediction. I'm not an expert on Kuhn, so whether this allows the qualification paradigm shift, I don't know, but I think it's maybe not so different.
But this is the normal way how science proceeds.
Right? Okay.
So what is so special about it?
I see. Yes. Okay. Fine. I'm happy with that. Yes. George.
Yeah, I have a question for Frank, and it's a question about terminology. In articles, one keeps seeing words like bridging, symbolic and sub-symbolic, combining symbolic and sub-symbolic, integrating symbolic and sub-symbolic, all in the glorious quest for the holy grail of getting the best attributes of both. In your excellent talk, you already hinted at the hierarchy. In other words, there's at the top is the truly integrated world model that is partially symbolic and partially sub-symbolic. Then at the lower level, there is what Wolfram is advertising, using words like integrating LLM technology into the Wolfram mathematical computing machinery. But that seems to be piecing together at a much lower level, and there are probably intermediate levels in what you referred as a front-end interpreting and then handing over. So is there any value in sort of being more precise about a hierarchy and the terminology that goes with it?
I'm also interested to hear what the others think about this. You're right. Certainly I was very sloppy in using all those terms for similar and different things. My talk was in a way very limited because all I did was very loosely coupled ways of combining the two. I had a module that was doing data-driven learning, and I had a module that was doing knowledge-driven reasoning, and I combined them in different ways. Sometimes one was on top, sometimes the other were on top, sometimes they were communicating in equal ways, but they were always very loosely coupled. There is another school of thought that says, no, we should aim for a much deeper integration, that we no longer have a neural box and a symbol box, but that there is a much deeper integration. I didn't talk about that at all. I think that is much harder. There's probably people in the room working on that. So in a way, what I did was the low-hanging fruit, and I think a much deeper integration will be harder, but maybe more promising. Does that answer your question?
Well, I think in natural language processing, it's very clear that we need learning. That's absolutely important. So we cannot handle natural language with rules. So we need learning. Also in perception, we need learning. So we can't handle hearing, like speech recognition, with rules. Vision, we can't handle it with rules. So the big paradigm shift really in natural language processing was this going away from rules, going to learning. And this learning aspect is so important. And also when we go further and say, okay, language is just a part of communication, interaction, we have this situated system in order to understand what's going on and to learn what's going on. This combination of a body in a real situation with the perception and action capabilities. And this needs learning because we can't model it. And I think this is the important thing, really, and the big paradigm shift.
And then, Gerhard, if I understood you correctly, you have yet another idea about how to combine the two. If I understand you correctly, you say something, okay, we have the first principles of physics and engineering. From there you can derive equations, the structural equations or differential equations. Then you know, let's say, the general structure of your process. And your idea is to use, let's say, learning sub-symbolic approaches to find parameters. So basically what is called, I think, model identification. So maybe you could comment on that?
Yeah, I mean, this is obviously one point. Yeah, the other point is how to complete the models. A model, so modeling. If you look at the engineers, if they do physical so models of a technical system, so it's also not rather an art. Yeah, so it's like programming. Yeah, to find the right models which then work. Yeah, and unfortunately, real systems are that complex. Yeah, that you cannot sufficiently model this. So maybe some of you know Johann de Cleer. So he's one of the father of model-based reasoning and diagnosis. He worked at Xerox, and even the physics of these printers, the Tintenstrahldrucker, the
photocopiers.
No, the inkjets, yeah, the physics of the ink. So they somehow designed this, yeah, and as soon as this thing was working, produces and ship it. Okay, so the big problem is that we have some limits in describing things. Yeah, we think we are so smart, yeah, and can describe the world, and we have all these great theories, yeah. But it comes down to really model this in a sufficient way, yeah. Then we need a lot of trials and errors, yeah. And I think this is how we can proceed, yeah, in solving practical problems like diagnosis, for example, or designing. Designing is extremely important because the design costs are growing super polynomial, yeah, if you look in industry.
I fully agree, because I model nuclear reactions, which are really complex things, and you don't see them. They are not at our level. I think Thomas has the right to be. He was the first speaker. Now you are the last speaker.
Thanks. Is it working? Yeah, I'll try and keep it short. Seeing that truly awful charts, I think they came twice from the article from Communications of the ACM. Almost made me feel like I was being personally trolled. Here we are, the digital humanism, and I'm very happy that you have invited at least one actual humanist for your program today, and I know we have a philosopher tomorrow, and that is so unusual in this context. I think the thing we see there, just with the making a historical claim from someone who has no interest in understanding anything about what happened in history or historical thinking or any respect for historical expertise, or for taking this idea from the history of science, which is being completely misused, or anything really. And that's so common. People feel sometimes some kind of vestigial need to invoke the idea of history, but mostly to say that we've departed from history, or we have a rupture with history, or history, you know, and that's as far as it goes. And as someone who is the chair of a history department that has some responsibility for this beleaguered discipline, it's rather dispiriting, but again, I'm glad that we have some humanism here in digital humanism, and basically to the rest of you, I just, you know, if you ever feel like making a historical argument or grounding something, like, read some actual historical literature, maybe find a historian, you know, talk to somebody. It's not the most respected kind of expertise in the modern world, but I think it's a very relevant perspective on things. And again, I'm glad that, like, here today, at least, you know, you put me on the program and gave me the first word as a real historian, and as it happens, the last word as well. So thank you for that.
Okay, thank you very much. I would like to thank the panel. I would like to thank the audience for their involvement. I hope that we made a few steps away from what was this morning called antagonistic view on things symbolic versus sub-symbolic. But those who like this antagonistic stuff and competition, then Ludger and Hannes can announce the winner this night. Okay.
We have another day tomorrow.
We have another day tomorrow, and see you then.